In this presentation, we'll go through the three different ways that speech is typically displayed visually with graphs. Sound's invisible, so there's no way to look at it directly. Rather, we record sound using a microphone and then analyze and display that recording. Sound is the result of displacement of air molecules. If that displacement happens within a certain frequency range, around 20 to 20,000 hertz in humans, then we can hear it. Sound is analyzed using acoustic measures. The three main measures are frequency, amplitude, and duration. Additionally, phase can sometimes be measured and is important for specific things like how we hear what direction a sound is coming from. The measures that we make of sound can be displayed graphically so that you can look at representation of a sound on a computer screen or in a research article. Depending on what the sound display shows, it has different uses. For example, some displays make it easier to see duration, while others make it easier to see frequency. The sound pressure waveform shows the amplitude of a sound as it changes over time. The amplitude is plotted vertically up the side along the y-axis. Amplitude is measured as pressure or intensity. Unless your equipment is calibrated, an absolute measure of amplitude isn't possible. So in the PROT program, for example, that you will use for homework assignments, there are no units given for the amplitude. In PROT, the amplitude scale goes from a maximum value of +1 to the minimum value of -1. Zero amplitude is a neutral pressure, the pressure of the air in the room. Air pressure can be higher or lower than this neutral pressure, positive amplitude if it's higher, and negative amplitude if it's lower. In the sound pressure waveform, time is plotted along the x-axis from left to right. So the waveform shows how the sound pressure or sound intensity changes over time. This is measured at a single point in space, the head of the microphone that is recording the sound. Here's a sound pressure waveform of a simple periodic sound, a pure tone with a frequency of 200 hertz. Frequency is 200 hertz means there are 200 exact repetitions of the cycle of the sound up and down and back in 1 second. Here's a sound pressure waveform of an aperiodic noise sound. This sound has no repeating pattern. The amplitude is random from one moment to the next. You might think you can see some sort of pattern in the sound, but that's just because your brain really likes to see patterns. There isn't one. If you look at the spacing and height of the peaks and the troughs, it's very irregular. Here's a sound pressure waveform of a quasi-periodic sound, a real-world sound with repeating frequency components. Because it's a real-world sound, it doesn't repeat perfectly from cycle to cycle like a periodic sound does. But if you look at the pattern, spacing, and amplitude of the peaks and the troughs, there's a recognizable similarity from one cycle to the next. This happens to be a small piece of a vowel. The sound pressure waveform is especially good for measuring when things happen. It has a very precise representation of time for a sound. So it's particularly useful for measuring duration, how long a sound lasts. When measuring duration, you're measuring how much time passes from the start of something to the end of something, like a sound or one cycle of a periodic sound. To make this measurement, you would subtract the time when the sound starts from the time when it finishes. Like if you work from 4 p.m. until 12, you've worked 8 hours, which is 12 minus 4. Finish minus start. A duration is almost always positive because something can't take place for a negative amount of time. But you will sometimes see negative measures when the time of an event is measured relative to another. Kind of like a NASA countdown where they say t minus 8 minutes. That means you're at a point 8 minutes before lunchtime. Here's an example of a duration measurement from a waveform for a complex periodic sound. In this example, the duration of one cycle of the sound is being measured. As indicated by the brackets and arrows, we first find the beginning and end of a cycle. You can make this measurement in many ways. In this case, I chose points where the pressure was 0. The point on the left at 0.005 seconds is where the cycle begins at a pressure of 0. The pressure goes up, dips down, back up, then dips way down, and then comes back up to 0 to finish that cycle and start the next one. You could just as well start the cycle at its highest peak or its lowest trough. Any regular landmark works. In this case, the cycle ends at 0.01 seconds. So the duration is 0.01 minus 0.005, which is 0.005 seconds duration. One reason we would want to know the duration of the cycle is to use it to compute the fundamental frequency of the sound, in this case 200 hertz. The spectrum representation is a way to visualize frequency information in a sound directly without having to measure the duration to compute a period to calculate frequency. In a spectrum graph, the x-axis along the bottom shows frequency. Amplitude is shown up the side on the y-axis. Each point on a spectrum graph tells you how much amplitude there is in the sound at that particular frequency. Or another way to look at it is that each component of the spectrum graph shows you the amplitude of one simple periodic sound that is part of the total sound. This is an example of a line spectrum or a comb spectrum, a representation of the combination of simple periodic sounds that make up complex periodic sounds. In this case, there are many frequency components starting at 100 Hz, then 200 Hz, 300 Hz, and so on. As the frequency increases, the amplitude gets lower or rolls off. This line spectrum is an idealized version of what the noise generated by the vocal folds looks like. If you could take the vocal folds outside of a person and get them to phonate without the rest of the head getting in the way, you'd get a sound that looks somewhat like this. Comparing a waveform and a spectrum, we have two very different ways of looking at a sound. The waveform shows us change in sound amplitude at each moment in time, so we can precisely see when things start and end and measure duration. The spectrum shows us sound amplitude at different frequencies. You can read frequency information right off the spectrum. In order to measure a frequency, you have to watch sound change over time, so a spectrum shows us information for a window of time, not at some particular moment. A spectrum would be most accurate for sounds that are stable and don't change much over the interval that you're measuring. Here's an example of a line spectrum for a complex periodic sound with 3 frequency components. If we were to look at this same sound with a waveform, we could look at the periods to figure out the fundamental frequency, but we wouldn't be able to measure any of the other frequency components. With the spectrum representation, we see there are 3 frequency components, the loudest one at 700 Hz, with 2 others at 300 Hz and 1200 Hz. Here's a spectrum representation of an aperiodic sound. This is not a line or comb spectrum because there's amplitude at every frequency, not just a few components. This is true of all aperiodic sounds. It's a little counterintuitive, but if the sound is not periodic, it's not because it has no frequencies, but because it has all the frequencies all mixed together. In this particular example, there are some frequencies that are louder than others, which is true for aperiodic sounds in the real world. You may have heard the term white noise. That's an aperiodic sound with equal amplitude at all frequencies. This particular spectrum is something like what a sh would look like. It has a peak amplitude around 3000 Hz, depending a bit on the talker. Here's a spectrum for a quasi-periodic sound with 3 frequency components. You can see the 3 frequency components in the 3 sharp peaks. There's some noise as well, with amplitude between 0 and 20 dB for the frequencies around the peaks. This sound is really quite close to perfectly periodic. The amplitude of the periodic components is much higher than the amplitude of the other components. If you were to make a spectrum of a long steady-state vowel, like a tense vowel like ah, for example, it might look like this. The waveform is a very common way to look at speech because it shows duration so well. The spectrum is less useful in part because speech changes pretty rapidly. But we are really interested in the frequency information in speech. It's what differentiates different vowels like E from oo, or different consonants like S from sh. Because of this, the spectrogram representation was developed. In a spectrogram, time is shown on the x-axis like in a waveform. The y-axis is used to show frequency, like if you were to turn a spectrum on its side. In order to represent amplitude, the spectrogram uses darkness on a grayscale, or sometimes in color, with blue for low amplitude and red for high amplitude. Here's a waveform showing a recorded phrase in the corresponding spectrogram. Comparing the two, notice how they line up in terms of time. Where you see parts of the waveform with positive and negative pressure, there's darkness in the spectrogram at the same time. But the spectrogram shows more specifically how the amplitude can be different at different frequencies. Periods of time with frequencies that have high amplitude are shown in the darkest spots. Periods of time with frequencies that have low amplitude are lighter. The spectrogram shows how the blobs on the waveform can be very different in terms of their frequency. At the very beginning of the sound, there's a lot of high frequency information. It turns out that this is a s. A little later, around 0.5 seconds, there's a band of low frequency information. This is part of the vowel. It turns out that this is an E. This phrase is speech acoustics. One of the things you'll learn in this class is what the different speech sounds look like in a spectrogram. In this case, there are 3 S's in speech acoustics. Can you find them all? A spectrogram is created by making a whole bunch of spectra, the plural of spectrum. Since speech changes rapidly, those spectra are made for pretty short windows of time, usually 5 milliseconds or 0.005 seconds long. The spectra overlap. Usually each window starts 2 milliseconds after the previous one. One way to think about this process is that you're sampling the frequency information in the sound once every 2 milliseconds, which is a frequency of 500 samples per second. So you could see 500 changes in frequency in the sound over the course of 1 second. That's fast enough to capture how speech changes while we talk. This is what making a spectrogram looks like. For a waveform like the one you see here, we have overlapping windows, and we make a spectrum for each one. Since these windows are very short, there's not a lot of time to observe exactly how the sound repeats, so the frequency information we get is really a rough approximation. It turns out that this is a good thing. For the 6 example windows you see here, you can see how the frequency information does change a bit over time. In the first window on the left, there's one really low frequency component. After the first window, there's that low frequency component plus some higher frequency components. You can see where this comes from if you look at the waveform. For the first window, the wave is pretty flat. Starting with the second window, the waveform has a pretty high frequency ripple in it. That's what's showing up in the spectrum after the first window. To create the spectrogram display, those spectra are then converted into vertical strips of lighter and darker, because frequency is shown on the y-axis and amplitude is shown by darkness. So peaks in the spectrum show up as dark spots, and troughs in the spectrum show up as light spots. Here's another example of the relationship between a spectrum and a spectrogram. This is a spectrogram of the word speech, where the s, e, and ch components are each pretty easy to see. In between are silent gaps, which are the stop closure part of the p, and also the ch. For the s at the beginning, you can see the spectrum at the bottom has a lot of high frequency amplitude. This corresponds to the dark region at the top of the spectrogram. For the e in the middle, the peaks in the spectrum correspond to the gray strips in the spectrogram. For the ch at the end, what you see is pretty similar to the s, but there's more amplitude at middle frequencies. A few different basic types of sound are also marked on the spectrogram. Each looks a bit different. The near silence for the stop closure shows up as a mostly white vertical band. The quasi-periodic vowel sound shows up as something with vertical striation, reflecting phonation, and horizontal blobs of amplitude at different frequencies, which we will label as formants later in the class. The aperiodic noise sounds are fuzzier blobs with no regular vertical striation. There are also 2 spots, a bit harder to see, where sound abruptly onsets at the release of the p and the t part of the ch. These are aperiodic transient sounds. Given all the different things that go into a spectrogram, what you see on one can be controlled in a variety of ways. One of these ways is how the amplitude scale converts to darkness. This is called the dynamic range. While sound in general can have a very wide range of amplitudes, what is typical for speech is more restricted, and so we can get a better picture of what's happening in speech if we zoom in on the amplitude range a bit. When making a spectrogram, you can set how low you want the lowest amplitude that you can see to be. Anything lower than that will not show up, in other words, be white. This can be handy if there's some background noise in your recording. You may be able to set the low cutoff high enough that that noise doesn't display. Here's a visual for the dynamic range applied to a spectrum that is typical for speech. The low and high cutoffs can be set so that only the loudest parts of the sound show up as pure black. Only the quietest parts of the sound show up as pure white. By setting the dynamic range like this, we can show as much of the amplitude variation in the speech as possible over the grayscale. Here's what a change in dynamic range can look like in a spectrogram. In the spectrogram on the left, there are a lot of light gray areas where there's low amplitude of sound. In the spectrogram on the right, the low cutoff has been raised, making a smaller dynamic range, with the result that those light gray areas show up as white instead. Another parameter that can affect what a spectrogram looks like is called bandwidth. Bandwidth is literally the width of the frequency bands for the spectrogram, which affects how sensitive the spectrogram is to differences in frequency. A narrowband spectrogram would reveal very small differences in frequency, while a wideband spectrogram would smear those small differences together. You might think narrowband would always be better because it's more precise, but it's not that simple. The way you get precise frequency information about a sound is to watch it change over a long period of time. So a narrowband spectrogram has poor time resolution. In other words, if speech changes rapidly over time, a narrowband spectrogram would smear those changes together. As it turns out, a wideband spectrogram is generally more useful for looking at speech because it provides the most information about how speech changes rapidly without losing too much information about the frequencies. Since a spectrogram always comes from putting together a bunch of spectra, the difference between the broad and narrowband spectrogram comes down to differences between broad and narrowband spectra. Here are examples of what a broader band spectrum, a spectrum from a short time window on the left side, versus a narrower band spectrum, a spectrum from a long time window on the right side, look like. You can see much sharper frequency peaks in the narrowband spectrogram compared to the broadband spectrogram. When you take those shorter window or longer window spectra and put them together in a spectrogram, you can get a very different picture of what speech looks like. On the left is a broadband spectrogram of a vowel. It has vertical striations because the windows are so short that you see some changes in speech over the course of a cycle of phonation. In the narrowband spectrogram on the right, you see horizontal stripes, which are the different harmonic frequencies created by phonation. For most purposes, seeing that there is phonation in the vertical striation, combined with the blobs of gray at different frequencies from the broadband spectrogram, tell us more of what we want to know about speech. We aren't normally too concerned about harmonics, which is what we see that's different in a narrowband spectrogram. Typical parameters for speech analysis use a wideband spectrogram with 5 millisecond windows and a 50 dB dynamic range. This is accurate enough to see typical changes in speech amplitude and to see changes in the acoustics caused by speech articulation over time. Part of the reasons these settings are used is they tell us more about the configuration of the vocal tract for articulation and less about the configuration of the larynx for phonation. In the source filter theory of speech production that we will learn in this class, this highlights the filter, the vocal tract shape, rather than the source, the phonation. However, one reason to know about these settings is that they were developed historically mostly by looking at adult men. If you're measuring speech for a different population, like kids for example, you may need to adjust the settings. In summary, when applying displays of sound to speech, there are 3 common choices. The waveform display gives us good time information. If you're looking at a recording of a sentence, for example, you can see when different words or phonemes start and end, and you can get some idea of amplitude. If you zoom in closer to individual sounds, you can see from a waveform whether it is periodic or not, and can measure the period to compute fundamental frequency. The spectrum display gives us good frequency information as it directly displays different frequency components and their amplitude. We can see what type of sound we're dealing with depending on whether the spectrum has sharp peaks at a few frequencies, like in a quasi-periodic sound, or not, which would make it an aperiodic sound. The spectrogram display gives both frequency and time information, but it's not very precise for either, so you can see roughly different durations, but you really shouldn't measure duration off of a spectrogram because it's made out of a bunch of overlapping windows. Everything is smeared. You can also see broad frequency components and their relative amplitude. This is very helpful for differentiating different types of sounds and also for seeing how the frequency information changes over time, going from one sound to the next or within a changing sound, like a diphthong.